Welcome. Tonight, I invite you to silence the noise of the present and step into an age ruled by steel and pressure. Today, we will examine the thermodynamic architecture of Victorian steam engines and the invisible engineering details of railway logistics, from pressure valves to expansion joints, and from lubrication systems to track statics. We are diving deep into the heavy and methodical mechanisms that built the modern world. Prepare yourself for this technical journey into the heart of silence. The operational core of the Victorian industrial expansion lies in the precise management of phase transitions and the conversion of thermal energy into linear mechanical force. The Victorian steam boiler, primarily the Lancashire or locomotive type, functioned as a high-pressure vessel where the safety coefficient was determined by the tensile strength of wrought iron plates and the integrity of the riveting patterns. To maintain structural stability, these boilers utilized stay bolts to prevent the deformation of the firebox under pressures exceeding 150 pounds per square inch. The chemical composition of the feed water was a critical logistical parameter. Calcium carbonate and magnesium salts within untreated water would lead to incrustation, scale buildup, on the flue tubes, creating a thermal barrier that significantly reduced heat transfer efficiency and increased the risk of localized overheating and subsequent boiler explosion. The mechanical heart of the locomotive is the Walschaerts or Stephenson valve gear, a complex linkage system designed to regulate the cutoff point of steam admission into the cylinders. This process is governed by the principles of expansive working. By closing the intake valve before the piston completes its full stroke, the engine utilizes the internal energy of the expanding steam to perform work, thereby increasing thermal efficiency and reducing coal consumption. The synchronization of the slide valves was a task of millimetric precision, where the lead and lap of the valve determined the timing of the exhaust phase and the compression of residual steam, acting as a pneumatic cushion to decelerate the piston's reciprocating mass at the end of each stroke. The metallurgical durability of the piston rings and cylinder liners was managed through the constant application of high-viscosity mineral oils or tallow-based lubricants, delivered via displacement lubricators. In these systems, steam was condensed into oil reservoirs, displacing a precise volume of lubricant that was carried by the steam flow into the moving parts. The friction coefficient of the brass bearings on the driving axles was monitored through the detection of thermal anomalies. If the lubrication film failed, the resulting hot box could lead to the catastrophic seizure of the axle. The logistical continuity of the railway depended on these micro-level interventions, where the viscosity of the oil had to be adjusted seasonally to account for ambient temperature fluctuations. The civil engineering of the permanent way, the track, was a study in static load distribution and material elasticity. The bullhead, or flat-bottom rails, were secured into cast-iron chairs using compressed oak or teak wedges known as keys. These wooden keys acted as natural dampers, absorbing the high-frequency vibrations of the locomotive's unsprung mass. The longitudinal expansion of the rails due to thermal fluctuations was compensated by expansion gaps at each rail joint, where the fish plates were designed with slotted holes to allow the steel to slide without bucking. The ballast, the bed of crushed stone, served a dual hydraulic and mechanical purpose. It distributed the vertical load across the formation while ensuring rapid drainage of rainwater to prevent the softening of the clay substructure, which would otherwise lead to a pumping, sleeper, and track misalignment. In the logistical management of coal and water, the Victorian railway network operated as a thermodynamic circuit. The location of water cranes and coaling stages was determined by the consumption rates of the locomotives, calculated in pounds of fuel per mile. To maintain momentum, some high-speed routes utilized water troughs located between the rails, allowing the locomotive to scoop up thousands of gallons of water at full speed using a retractable scoop mechanism. This avoided the loss of kinetic energy associated with stopping, but required precise hydraulic calculations to ensure the water velocity was sufficient to overcome the vertical head of the tender tank. The Victorian era was not merely a time of progress, but a time of rigid mechanical discipline. Every hiss of escaping steam, every rhythmic clank of the connecting rods, and every expansion of a rail was a testament to the methodical management of physical laws. Within this stagnant and technical world, the machine and the road became a single, flawlessly functioning entity, carrying the heavy knowledge of the industrial past into the modern age. The evolution of maritime logistics in the late Victorian era was defined by the transition from simple expansion to triple expansion steam engines. This was a thermodynamic necessity to maximize the work extracted from every pound of coal. In these engines, steam was exhausted from a high-pressure cylinder into an intermediate pressure cylinder, and finally into a massive low-pressure cylinder before reaching the condenser. This cascaded pressure drop minimized thermal loss through cylinder wall condensation. The crankshaft of these vessels, forged from high tensile steel, had to withstand immense torsional stress. The alignment of the bearing blocks was checked using optical sighting and micrometer measurements to prevent crankshaft deflection, which would lead to catastrophic metal fatigue. To maintain the vacuum necessary for these engines to operate at peak efficiency, the surface condenser became a critical logistical component. Unlike earlier jet condensers, surface condensers utilized thousands of small-diameter brass tubes through which cold seawater was pumped. The heat exchange occurred across the tube walls, allowing the distilled feed water to be recovered and reused in the boilers. The prevention of galvanic corrosion within these tubes was managed through the sacrificial use of zinc plates, anodes, which were electrolytically consumed to protect the integrity of the brass. This was a silent, chemical maintenance protocol that ensured a ship could traverse the Atlantic without its boiler tubes failing due to salt contamination. Simultaneously, the Victorian logistical network was being revolutionized by the submarine telegraph cable, a marvel of material science and electrical engineering. The primary technical challenge was signal attenuation and inductive retardation over thousands of miles of submerged wire. The core of the cable was high-purity copper, but the success of the project rested on the insulation properties of gutta percha, a natural latex from Southeast Asia. Gutta percha was unique because it became more resilient and a better insulator under the immense pressure and cold temperatures of the ocean floor. To protect this core from the mechanical abrasion of the seabed and ship anchors, the cable was armored with a helical wrap of galvanized steel wires, bedded in a layer of tarred jute. The transmission of data through these cables was not a matter of high voltage, but of extreme sensitivity. Because long cables acted as massive capacitors, the electrical pulses would smear, making high-speed transmission impossible. To detect the faint, distorted signals, Lord Kelvin developed the mirror galvanometer. This device utilized a tiny mirror suspended by a silk thread, which would deflect a beam of light in response to the smallest electrical current. The light spot moving across a darkened scale was the primary interface of Victorian global communication. The signaling rate was measured in words per minute and was strictly limited by the RC time constant of the cable, a mathematical ratio of resistance to capacitance that defined the bandwidth of the 19th century world. At the receiving stations, the logistical management of information required a methodical standardization of cable code. To combat the high cost of transmission, complex code books were used, where a single five-letter word could represent an entire commercial contract or a specific engineering requirement. This was the first era of data compression, where the economy of the word was as vital as the economy of the coal. Every pulse of light in the darkened telegraph room and every stroke of the massive low-pressure piston in the engine room was a part of a unified global machine, operating with a precision that anticipated the digital age. The logistical survival of the Victorian metropolises, particularly London, was predicated on the construction of the intercepting sewer system, a monumental feat of civil engineering designed by Joseph Bazalgette. This system functioned as a gravity-fed hydraulic network, where the primary technical parameter was the hydraulic gradient. To ensure that waste reached the outfalls without stagnation, the brick-lined tunnels were constructed with a precise fall of 2 feet per mile. The structural integrity of these tunnels relied on the use of Portland cement, a relatively new material at the time, which was subjected to rigorous tensile testing. The egg-shaped cross-section of the sewers was a deliberate geometric choice to maintain a high velocity of flow, even during periods of low water volume, preventing the accumulation of sediment through self-cleansing action. At the discharge points, the management of massive volumes of fluid required the implementation of beam pumping engines, such as those at Crossness Pumping Station. These engines, with their massive 47-ton flywheels and ornate cast-iron beams, were thermodynamic giants designed to lift thousands of gallons of raw sewage from low-level drains to high-level outfalls. The mechanical efficiency of these pumps was governed by the duty of the engine, a measure of the work performed per bushel of coal consumed. The lubrication of the massive parallel motion linkages, a mechanism pioneered by James Watt, required constant manual attention to ensure that the vertical movement of the piston was translated into the arc of the beam without lateral stress. Parallel to the subterranean efforts of sanitation, the Victorian naval race introduced the ironclad battleship, a synthesis of steam power and heavy metallurgy. The primary engineering challenge was the armor-piercing capability of rifled breech-loading guns versus the resistance of compound armor plates. These plates were a metallurgical hybrid consisting of a hard steel face welded to a soft wrought iron back. The steel face was designed to shatter the incoming projectile, while the wrought iron back absorbed the kinetic energy and prevented the plate from cracking. The thickness of the armor and the carbon content of the steel were variables in a lethal mathematical equation, where every inch of protection added significant displacement to the ship's hull, requiring more powerful engines to maintain speed. The ballistics of the great naval guns were governed by the internal ballistics of slow-burning brown powder, cocoa powder. Unlike modern explosives, this powder burned at a controlled rate, providing a sustained push to the projectile as it traveled down the rifle barrel. The rifling itself, the spiral grooves inside the bore, imparted a gyroscopic spin to the shell, stabilizing its flight path and increasing accuracy over miles of open sea. The mechanical stress on the gun's trunnions and the hydraulic recoil buffers was immense. These systems utilized a combination of heavy springs and oil-filled cylinders to dissipate the energy of the discharge, preventing the gun from tearing itself off its mountings. Whether deep beneath the city streets in the brick-lined silence of the sewers, or amidst the thunderous fire of an ironclad's battery, the Victorian era was defined by a relentless pursuit of technical control over the physical world. Every brick laid in a perfect arc, every stroke of a pumping beam, and every rifled groove in a steel barrel was a calculated step toward a fully engineered reality. Within this world of high-pressure steam and heavy iron, the precision of the calculation remained the ultimate arbiter of success. In the logistical management of deep-shaft coal mining, the primary technical challenge was the ventilation of the workings to prevent the accumulation of fire damp, methane, and choke damp, carbon dioxide. Before the widespread use of mechanical fans, the Victorian solution was the furnace ventilation system. At the base of a up-east shaft, a massive furnace was kept burning perpetually, heating the air and creating a powerful thermal updraft. This established a pressure differential that drew fresh air down the downcast shaft and through miles of tunnels. The flow of air was directed using a complex network of trap doors and brattice cloths managed by boys known as trappers. The volume of air, measured in cubic feet per minute, had to be carefully calculated to ensure that the air velocity was sufficient to dilute explosive gases, but not so high as to extinguish the miner's safety lamps. The safety of the miner depended on the Davy lamp, a masterpiece of thermal physics. The lamp utilized a fine wire gauze screen to surround the flame. The technical principle was based on the thermal conductivity of the metal gauze, which dissipated the heat of the flame so rapidly that the air outside the gauze never reached its ignition temperature, even if the gas inside the lamp ignited. The mesh count of the gauze, typically 784 apertures per square inch, was a standardized technical parameter. A miner could monitor the gas cap, the blue flame halo, inside the lamp to gauge methane concentrations, making the lamp both a source of illumination and a rudimentary chemical sensor. Above the Earth, the Victorian quest for precision reached its zenith in the construction of great refractor telescopes. The optical performance of these instruments was limited by the chromatic aberration of large glass lenses. To solve this, master opticians utilized achromatic doublets, combining a convex lens of crown glass with a concave lens of flint glass. The refractive indices and dispersion coefficients of these two glass types were mathematically matched so that they canceled each other's color distortions, bringing different wavelengths of light to a single focal point. The casting of these glass discs, sometimes exceeding 30 inches in diameter, required a cooling, annealing process lasting several months to prevent internal stresses that would lead to optical birefringence. The mechanical mounting of these massive telescopes required the engineering of the equatorial drive. To track a star as the Earth rotated, the telescope, weighing several tons, had to move with sub-millimetric smoothness. This was achieved using gravity-driven clock drives, where a falling weight powered a train of precision-cut brass gears. The speed of the descent was regulated by a centrifugal governor, ensuring a constant rotational velocity. The telescope's axes rested on friction-relieving rollers or primitive ball bearings, lubricated with refined whale oil to minimize the stiction that would otherwise cause the image to jump in the eyepiece. In the laboratory, the compound microscope reached a similar level of maturity through the development of oil immersion objectives. By placing a drop of cedar wood oil between the lens and the slide, microscopists could match the refractive index of the glass, eliminating the light loss caused by air-to-glass transitions. This increased the numerical aperture of the lens, allowing for a resolving power that revealed the microscopic world of bacteria and cellular structures for the first time. This was the final frontier of Victorian measurement, the ability to observe the infinitely large and the infinitely small with the same methodical, mechanical certainty. The logistical challenge of transporting perishable proteins across oceans necessitated the development of marine refrigeration systems, specifically the cold air machine Bell-Coleman cycle. Unlike modern chemical refrigerants, these early systems utilized the atmospheric air itself as the working fluid. The technical process relied on the adiabatic expansion principle. Air was first compressed to a high pressure, which increased its temperature. It was then cooled by seawater heat exchangers and finally allowed to expand rapidly in an expansion cylinder. This expansion caused the air temperature to plummet to as low as 60 degrees Celsius. The dry, frigid air was then circulated through the ship's insulated holds, lined with layers of charcoal or silicate cotton, mineral wool, to minimize thermal leakage. This was the thermodynamic triumph that allowed the Victorian world to decouple food supply from local geography. In the heart of the Victorian metropolis, the problem of rapid internal communication was solved through pneumatic dispatch networks. These underground systems of lead or iron tubes through which telegraph forms and small parcels were propelled using air pressure or vacuum. The physics of these systems was governed by fluid flow in pipes and the management of pressure differentials. Massive steam-powered air pumps, located at central stations, maintained a constant vacuum in the down tubes and a positive pressure in the up tubes. The carriers, typically made of gutta percha and lined with felt, had to maintain a near-perfect seal against the tube walls to prevent pressure bypass. The travel time was a function of the tube's diameter and the pump's displacement capacity, allowing messages to traverse the city at speeds exceeding 30 miles per hour, bypassing the surface congestion of horse-drawn traffic. The Victorian thirst for information led to the development of the rotary printing press, moving away from the slow reciprocating action of flatbed presses. The technical innovation lay in the stereotyping process, where a flexible flong, a papier-mâché mold, was taken from a flat page of type and then cast into a curved lead plate. These cylindrical plates allowed for continuous rotation, enabling newspapers like the Times to be printed at rates of 10,000 sheets per hour. The synchronization of the paper feed, using massive web rolls of continuous paper, required precise tensioning mechanisms to prevent the paper from tearing under the centripetal force of the rotating drums. The viscosity of the ink was also a critical variable, adjusted to dry almost instantly upon contact with the paper to prevent smearing at high speeds. Finally, the Victorian mastery of force reached its peak in the hydraulic power networks. In cities like London and Manchester, high-pressure water was distributed through miles of cast iron mains as a utility, similar to electricity today. This water, pressurized to 700 psi, powered the lifts in hotels, the cranes in the docks, and the stage machinery of theaters. The stabilization of this pressure was managed by the hydraulic accumulator, a massive vertical cylinder containing a weighted ram. When the demand for power was low, the pumps lifted the ram. When a crane was activated, the falling weight of the ram forced the water into the system with constant pressure. This was the first large-scale energy storage system, a mechanical precursor to the electric grid, providing a silent and immensely powerful source of torque to the entire city.